we have been discussing the number of the transport of charges from iron surface to the metal surface and transport of metal atom from metal surface to iron surface in the solution. And on that way we have seen that if these are the two surfaces and then this is metal surface and this is metal N plus, and the reaction, if you consider equilibrium N plus plus N E M, for this equilibrium the iron is coming from this surface to this surface and metal atom is going from this surface to this surface, and this transformation, this transfer of species is not a very simple process. It does not go like this. It has to cross a barrier, and that barrier is nothing but the activation barrier. And we have already seen that if you draw a G versus free energy versus a distance plot, now here you have a well, and now you have to, this is my second position. Now, if and this metal atom, it will move across this barrier and metal charge will also move across this barrier to come to this side, and we have seen that this is my free energy barrier. And we have started having some sort of equation with respect to the free energy barrier as a function of free energy barrier, as a function of number of moles per unit area on this surface or on this surface, and with the vibrational frequency of atom or charges. And then we have also included a part which is a f. F is nothing but the small f is nothing but the fraction of atom. Let us say from here to there, the atom is moving from this surface to this surface and it is forming charge. The fraction of atom which is actually going and sitting there. Now, we have seen that if you consider the flux, now we have to see the flux of moles or the species transferring from this surface to this surface or this surface to this surface, and this if we consider that is the forward reaction. Now, if let us say this is my forward reaction and this is my backward reaction, then the forward reaction flux would be equal to, we can consider R1 is nothing but, or flux is nothing but the rate of transfer of species per unit area per unit time would be equal to N1 F1 N1 nu 1 exponential minus del G star by RT. Now, similarly, we can put this is, if you consider R1, this is R2. R1, this arrow means it is a forward direction rate or flux, and this is the backward direction rate or flux. Similar way, R2 would be equal to N2 F2 N2 nu 2 exponential minus del G star by RT. And we have also seen that if these two rates are same, we can equate these two equations, we will get an important relation which is F1 N1 nu 1 equal to F2 N2 nu 2. And also we will see that this F, generally the value is roughly considered to be 1, nu is around 10 to the power 12 to 13 per second, and N1 and N2, if let us say the charge, the number of charge which is coming from this to this or metal atom going from metal atom to this, these two are equal, and if you consider unit area, let us say 1 centimeter square area, let us say this is 1 centimeter square area, this is 1 centimeter square area, and also this is my 1 centimeter square area. Now, I will also see that N1 and N2, they are not they will not, if we assume that these two are same, then this is basically all the time, even if there is some sort of non-equilibrium or the rate of forward direction or rate of backward directions, these two are different. The only change would be here, this term will remain constant or fixed. Now, if these are fixed, now we know what is my rate equation as a function of current density. We know that the current density part, if we remember the previous calculations, we know that dn dash dt dn dash dt by 1 upon nf dq by dq dt, since this is basically the charge transfer rate and this is the rate at which number of moles are transferring from metal surface to iron surface. Now, this we can write in the form of per unit area. So, I can divide it with area term, which is nothing but A. Here also I have to divide it with area. Now, this is nothing but the current. So, now this is n dash A dt equal to I. Now, this by this is becoming I, small I by nf. Now, this term is nothing but, so this term is nothing but this, because the unit of this is number of moles per unit area per unit time. You see that this unit is also same if n dash is the number of moles. So, this is nothing but R1 or R2 equivalent to R2 equal to I by NF. Now, this I, if these two are equal, here I have put equivalent, means equivalent, their units are same. Now, if these two rates are different, R1 and R2 are different, so they will not be equal, but if these two rates are equal, then R1 equal to R2, I can write it. Then I know that when this has reached equilibrium, and if the activity of this species is 1 unit activity, if we maintain all those species, then this is nothing but the non-corroding system, and the potential developed will be standard reduction potential, which is nothing but E0 m n plus m. And when we have already seen the concept of exchange current density, that exchange current density, it says that when the system is at is in equilibrium and non-corroding system, or the reversible condition where you do not have a net formation of metal ion, and net formation of metal ion is nothing but the corrosion. So, that since there is no net formation of metal ion, whatever metal ion is forming, that metal ion is getting deposited and there is an equilibrium. So, that non-equilibrium, that non-corroding system reversible equilibrium condition, I can think of exchange current density of this reaction on the surface of the metal, and that surface is nothing but the same metal surface. So, this is here I can consider I0, I can write on metal surface, and this is, so exchange current density for this reaction on metal surface M. And this thing I can write, I can have a correlation if we consider the reverse and forward direction reaction rate. So, R1 equal to R2 equal to I0 NF. So, I can write I0 NF. Now, if I put this I0 NF instead of R1 or R2, since these two are equal in the equilibrium, so I can get I0 equal to NF N1 nu 1 F1 exponential minus del G star by RT. And if you see that this term is basically a fixed for this case, because N, F both are constant for this particular reaction, and we have already seen that this is equal to this and this value does not change much, and we can assume that this is with a reasonable assumption we can have, that is F1, N1, nu 1 are fixed value in this case. So, now we can say that I0 is nothing but A dashed, we will consider it as a constant. So, this A dash, this all the things are included in this A dash. So, I can have a good relation for this exchange current density. Now, this relation will come into our, or it will be an important issue when we consider polarization. Now, I have included this word polarization. Now, let me come to this term, or it's a polarization. Let me talk about polarization now. And this polarization, this equation would be an integrated part of the polarization equation. Now, let us say I have this reaction, this is my equilibrium reaction for metal deposition as well as metal formation, metal ion formation. Now, that case, this is nothing but IC, this is nothing but IA. We have already come to see this is the cathodic current density, this is anodic current density, and there would be a negative sign here, and if it is equilibrium, so IC equal to IA equal to I0, which is exchange current density. Now, what happens if there is a net metal ion formation? Now, net metal ion formation, it means that the equilibrium is disturbed, and if equilibrium is disturbed, I can write it in the form so that means equilibrium is disturbed. So, I have preferentially this reaction. It does not mean that the backward reaction is stopped, backward reaction is also happening. So, if you consider this is to be R2 dashed, so backward reaction R1, this is basically in this case this is my R1 forward reaction and this is my backward reaction. Now, in this case I know that equilibrium is disturbed and metal ion formation is preferred. So, I am having preferentially metal ion formation, but since that means that R2 is greater than R1, and that means the rate at which the metal ion is forming is exceeding the rate at which metal ion is getting deposited. So, you have a net metal ion formation, and in that case for the net metal ion formation you have to see that you have to take the current charge or the electron from the metal at a faster rate, and for this if we know that this is the metal ion formation. So, corresponding current is nothing but IA, and it means that IA should be greater than IC. I am taking the mod value because just to avoid the negative sign. If IA greater than IC, then R2 would be greater than R1, and when it happens you will see that the potential is deviating from the equilibrium potential, and the potential here also you will see that here you have this is E0 m n plus m, this is E0 m n plus m. So, this potential which is existing here, if you have preferentially this reaction, then you will see that potential for this reaction is changing towards the positive side. So, you can also measurement of the potential for this if the deviation is taking place in the potential. So, let us say after some time the potential become E for this, you will see that E1 E dash minus E0 m n plus m, it is a positive quantity. It is a positive quantity. That means, because of this disturbance in equilibrium or because of the preferential formation of metal N plus for ion, you are deviating the potential from the equilibrium value to some positive value, that is why this becomes positive. And here we are considering only the reduction potential. So, reduction potential goes from E naught, which is equilibrium potential, to a higher potential. Similarly, if you have deposition reaction at a faster rate, that means R1 should be greater than R2. So, IC should be greater than IA. So, deposition rate is faster than the production rate of metal N plus. And in this case, this is case number 1, and in this case, this is case 2. You will see that after some time, if you measure the potential E double dash, and if you find out what would be the difference in potential from the equilibrium potential, so this minus E naught m n plus n m would be negative value. That means, in this case, if you have a deposition reaction or the reduction reaction at a faster rate compared to the production reaction or the metal ion formation reaction, then potential goes towards the negative side from the equilibrium potential. And who is the culprit for this transfer of equilibrium potential from positive to negative or negative to positive? For example, here potential goes towards the positive side compared to equilibrium potential. In this case, potential goes to the negative, towards the negative side compared to the equilibrium potential. So, who is the culprit? The culprit is preferential transfer of electron. In this case, case 1, the electron is taken away from the metal at a faster rate than the consumption, and in this case, where IC greater than IA or IC greater than IA, the electron is getting consumed by metal ion at a faster rate compared to the electron generation. So, and charge transfer is nothing but the current. So, whenever you have a current flow, then you will see that the potential shifts, and potential shifts from the equilibrium value, and this shift in potential is nothing but the polarization from the equilibrium value. So, how do you define polarization? How do you have a conceptual, how do you have a concept of polarization? Polarization implies deviation of potential from equilibrium potential because of current flow or charge flow net charge flow. I should mention net charge flow, because when you have equilibrium then also charge flow is taking place, but the rate at which charge is flowing for the forward reaction as well as backward reaction, this is the same. And when you have polarization, you have a net electron flow. In this case, electron is basically you are taking away from the metal at a faster rate, and in the cathodic case where IC is greater than IA, we consume electron at a faster rate than the production of electron. So, this is my concept of polarization. Now, we see that in this case, case 1, I have a positive quantity, we call it as anodic polarization. And in this case, it is cathodic polarization. Now, the point is, how do we quantify polarization? The polarization is quantified in the form of overvoltage. And it is given as this form neta. Now, the overvoltage, in this case, the overvoltage is nothing but the difference between the final potential and equilibrium potential. So, in this case, this is a positive quantity, so I can term it as anodic overvoltage, and in this case, I can term it as cathodic overvoltage. A subscript A means anodic, subscript C means cathodic. So, here anodic polarization or anodic overvoltage, and this is cathodic overvoltage. And if you would like to see what would be the sign, so if this is Na is positive, so Nc would be neta C would be negative. So, this is positive and this is negative. So, this is concept of polarization and overvoltage. Now, getting back to this picture, we know that the metal ion surface is forming, metal is forming, and this picture, if you can see what is happening from the start of the reaction, let us say you have dipped a metal in a solution where you have metal ion already existing or salt of metal is existing. So, you can have an equilibrium. Now, when you have that, let us say first thing is there would be formation of metal ion from metal, and similarly metal ion would go into the metal. So, there would be a sort of equilibrium or dynamic equilibrium that would be existing at constant pressure and temperature, or the temperature or pressure that in that condition there would be an equilibrium. Now, when you have that, when you form metal ion, it will always be solvated by water molecule, because it is a positive charge. So, solvation will occur. So, you have positive. Now, you can have this water molecule will encompass the positive charge, and because this is water molecule has a polarized effect. So, there will be dipoles, and these dipoles, the negative side will come close to this positive side. So, this is nothing but the solvation. So, you have a solvation there. Now, also you have left electron at this surface. So, there would be, so you have positive charges here, there would be negative charges here. So, you see there would be a formation of capacitor. This is the negative side, this is the positive side of the capacitor. And also this surface is called as inner Helmholtz plane, and this is called outer Helmholtz plane. And H here it is Helmholtz. So, this side is inner Helmholtz plane, this is a plane and this is outer Helmholtz plane. Now, we know that if this is at equilibrium, so you have this sort of formation of reaction barrier, or this is the activation energy, and that time if you would like to see what is my relation between the rate flow or the flux from this to this surface, out inner HP to outer HP. So, you can come across the concept of exchange current density. Now, when you have preferential metal ion formation, or you are breaking this equilibrium and you are increasing IA compared to IC. So, IA greater than IC if you consider their value, or other way around if you consider the reduction process, that time IC would be greater than IA, and that case polarization will occur. So, what would be, how can we measure IA and IC as a function of overpotential? Now, that thing, let us have a relation. From this we can have a relation from with respect to overpotential and current. What is current? Current is the kinetic part, and overpotential is nothing but the difference in potential, and potential is nothing but a thermodynamic quantity. So, we have to relate overpotential or the polarization with the current value. Now, let us consider this plot again. Let me put it here, let me remove this part, let me draw it here. Now, this is IHP and this is OHP. When this is at equilibrium, that time I will have this is my let us say this is my free energy, this is distance, this is IHP, this is OHP, and now here what we have? We have metal atom in the elemental condition, and that we are putting as 0. 0 means this not value means it is in, we are considering the equilibrium concept. Now, that case this level and this level both will be same because it is in equilibrium. So, the state here and the state here, the free energy state and the free energy state, both these cases would be same. So, that is what they are at equal distance from the reference distance, from the reference plane, reference value. Now, this side I can put it as M 0 M n plus. This 0 I am putting just to indicate equilibrium. Now, when and this is IA and this is my IC with a negative sign, just to indicate that the rate, forward rate is given as IA, backward rate is given as IC, which is the cathodic process. Now, you disturb this equilibrium. If you disturb this equilibrium, you can see that this would be greater than this. That is what we have seen. If this is greater than this, now we know this relation. If you see this relation, in this relation, if this term increases, this term would go down, and if this term decreases, this term will go up. Now, since I know that IA is greater than IC, which is the anodic process, this is IA is greater than IC. So, I should see that the barrier, reaction barrier should decrease for the anodic process or the metal ion formation process. Then only this would be higher, this would be higher than this. So, what would be the rate of backward reaction? Let me put it as backward reaction would be equal to, same way I can do the whole treatment, but since we know that this is considered as A dashed, I can put it as A dashed. So, I can put it as A dashed exponential minus del G star by RT. Now, here I should see that this is, let me put it as A again here, just to indicate that this is the anodic reaction rate. So, this A or this I am correlating with this. Now, that case my distribution of the figure, this figure would change. How would that change? So, I should see that overall value of this should decrease. Similar way, this would go down. So, overall value of this side would increase. So, if I have a process like this, let me put it in a different color. So, what would be my barrier? My barrier would be this much for the forward reaction. And similar way, I should see that the barrier for the reverse reaction, that means this one should topple this barrier and this barrier should increase. So, my distribution of the curve would be like this. So, that case my barrier for the reverse reaction or the IC would increase. Now, this may, let me put it as del G A and this let me put it as del G C. So, instead of del G star I should put del G A. Just let me consider only the for IA value with respect to anodic process. Now, what would be the value of this? And we know that this one is del G star. Now, if any number of electrons are involved for this process, and let us say I have a fraction f alpha, which is the symmetry factor for this related to this diagram, and if we consider that this is my total over voltage, and then this is alpha fraction of this total over voltage is contributing towards the anodic polarization. So, then what would be my anodic polarization if this is my total and this is my alpha, which is the fraction of the total polarization that is coming as anodic polarization. So, my anodic polarization value would be and here alpha is symmetry factor, or it can be called as the extent of polarization of cathodic anodic process. So, if alpha is the extent of polarization for the anodic process and this is my total polarization, then what would be my anodic polarization value? Alpha neta. And this polarization is happening because we have already disturbed this equilibrium. So, no longer I am having this equilibrium and we are having this process where this rate is more than the reverse rate. And when you have that this process, that time I know that alpha is the extent of polarization. So, my total anodic polarization would be alpha neta. Now, if this is my polarization, which is basically nothing but volt, what would be the energy associated with or the free energy associated with it. Now, I know that the free energy is nothing but minus NF E, and what is the voltage here? Alpha newton. So, I know that what would be my free energy change? Alpha newton. So, my free energy change would be this, and now let us see whether the free energy change is positive or negative. Here I lift the potential of this MO to, let me put it as MA, which is in activated condition or anodic polarized condition. So, that case this is my level. So, I have reduced the barrier. So, that case I should decrease, I am decreasing basically the overall activation barrier is decreasing by the amount of this much. So, the value of this would be this minus this. So, there would be a negative sign associated with it. So, we see that this is my nothing but GA, which is this is my free energy change for this anodic polarization, and that should be this part, and this is nothing but del G. Del G A would change to del G star minus this, del G star minus alpha N F beta. So, I know I am coming to the value of R A. There is a small mistake here. You see N dashed is nothing, this NF part is included in this part. So, then you can term it as I0. So, I can put it as a different constant which only constitutes, see, A double prime is nothing but N1 F1 nu 1. So, R A, which is the anodic rate, so that is nothing but A double prime exponential minus this. So, then what is my relation between I A and R A? R A, which is nothing but moles, number of moles per unit area per time, would be equal to I A by N F. Would be equal to A dashed double dashed, which is nothing but N1 F1 nu 1 into exponential. I can rewrite these two things, del G star by RT into exponential minus, so it will get cancelled, it will become plus alpha N F ta by RT. Now, I can write it. So, this would be equal to I A would be equal to N F A double prime exponential minus del G star by RT into exponential alpha N F meter by RT. So, what is this? This is nothing but I 0. So, I can write I A equal to, I can write I A would be equal to I 0 exponential alpha n f eta by R t. Now, you see that the anodic current, which is nothing but the rate of electron transfer from the metal, or the rate at which the electron is taken away from metal to form metal ion formation, to form metal ion. So, that is my I A, that current value, current density for anodic process, and that lead to polarization or the shifting of potential. And here also we see that shifting of potential, we have already seen the shifting of potential for the anodic polarization is positive, and we see that the polarization value and this term is coming positive. So, I can write would be equal to R t alpha n f ln I A by I 0. So, I can have the polarization or the amount of polarization or over voltage for the anodic process from if I know the current density, and the current density can be easily found out experimentally. So, if this is my expression, now since I have I A here, which is anodic process, I can easily term it as N A, which is nothing but the anodic polarization. Now, the confusion starts. Confusion is, initially we started with total polarization, the neta is considered to be total polarization. Now, I am considering as anodic polarization. You will see that whenever you have a high rate of forward this reaction, or if you see that I A is very much greater than I C, because of this I C, the polarization or the cathodic polarization would be very much negligible compared to the anodic polarization. So, if I A value is very large, so N eta total would be equal to eta A. You will see that, later we will see that. So, I am straightway putting anodic polarization, and this relation is the relation between the anodic current density or the rate at which anodic process is taking place, that would be related to the over voltage or the anodic polarization through this equation. And generally this symmetry factor is considered to be half. So, symmetry factor is considered to be half. So, 0.5, and we know R, we know T. If we know the T at the temperature where this process is taking place, we know this N F are constant for this process. So, this term we put it in terms of beta. So, that case I can write beta, I am putting A value because I am considering the anodic process, ln I A by I 0. Sorry, a small change. I can write N A equal to, I have to convert this ln part into log. So, R T into 2.303 by alpha N F log of I A by I 0. So, this part we put it in the form of beta, I 0. So, I can write it like this, I neta A would be equal to beta A log of IA minus beta A log of I0. You see this beta A, if you consider alpha to be symmetry factor, if you know this process in F, both of those are constants, R is also constant, gas universal gas constant, T is the temperature at which the process is taking place. So, this beta is a constant. Again I0 for this process on that metal surface in the solution is also a constant. So, this is a constant. Now, if you would like to see this, so this expression you can straightway write in this mode. I can put it as a constant C. This C is a constant here. This equation is known as Tafel equation. This equation is known as Tafel equation, where A is the Tafel constant, and this unit of this Tafel constant or the Tafel slope, this is Tafel slope is volt per decade of current density. Why per decade of current density? Because I am considering log of IA. So, this unit would be volt per decade of current density. And this is Tafel slope. Beta A is Tafel slope. And this is a very, very fundamental equation which relate over voltage with current density. Now, similar way we can have a relation between IC and over voltage, cathodic over voltage. So, that case we have to start from the you have to see the reverse process, and the reverse process, what would be my cathodic polarization with respect to the total polarization neta. So, that case I should see that this value is to be added. This value is to be added, because then you have to start from this, and that time this I can write it as M A M C N plus. C is nothing but I am putting it in the form of cathodic side. So, this is cathodic side, this is anodic side. So, that case my total free energy that is to be put in this equation is nothing but del G star plus this, and I am putting 1 minus F 1 minus alpha. That means that if alpha is the extent of anodic polarization, and we know that anodic plus cathodic polarization is nothing but the neta. So, now the relation is this is total Na plus Nc. So, now if this contribution is alpha, so in this case it would be 1 minus alpha. So, extent of 1 minus alpha plus alpha equal to 1. So, this concept also, this is also right. So, the N A would be the overall with respect to overall or the total polarization would be 1 minus alpha N F neta. So, that case I just replace del G star with del G star plus this, and if I do the same process I will get a relation see that case Tafel slope, anodic Tafel slope, since I am putting A here, So, this beta C is basically nothing but cathodic and C dash is constant here. And if you would like to see the value of beta C and beta A, so let me put the value here. And here is it is fine. So, now we know this equation, and this equation also relates a thermodynamics with the kinetics of corrosion process. And what is the corrosion current here? Corrosion current is nothing but the IA, which is the formation of metal ion, the current associated with the current density, which is associated with the metal ion formation. So, now we know these two relations. Now, if we would like to see the polarization effect, let us say I am at this position where I know that this equilibrium is existing. So, that case what would be my, let us say this is my log I, what would be my current density, the rate of forward or backward process, that is nothing but I 0. So, let me see that I am here. Okay. Now, what would be the potential here or the polar, let us say I am putting the over voltage. What would be my net over voltage? The net over voltage would be 0, because at this condition when it is at equilibrium, I know that potential always will be standard reduction potential. So, now if I would like to see that if IA is increased compared to the IC, so it would go into the anodic polarization side. That time I have to consider this equation. And now this is a straight line equation with a slope of beta A. So, I will see that the line is like this. That time this is C. Now, let us say that time IA is greater than IC. And if I would like to see if potential goes to the negative side, this is positive side, this is anodic polarization. So, I can see that this is Na, I am writing positive. Now, if I see that cathodic current density is more than the anodic current density, so it should move towards the negative side compared to the standard reduction potential or the reversible potential. So, again this will follow this equation. That time I will see that this is my cathodic side negative, the equation would be C dashed. So, I see that if I have preferential anodic process, I will move towards this. If I have preferential cathodic process, I will move towards this. Thank you.